Sorry. The easy questions on the exam. So the question is, are we going to have easy exam today? So I let you know that when I'm not bragging. It will sound like bragging, but it's not bragging. In my senior year, I went, and that was like the final. Okay, I went to the professor after the exam. So like we have a big class, 120 students. And we will have the class in one place. The professor does not come to the exam. So we have the exam in the aerospace department, and then we go to the mechanical where the professors are. And so anyway, I went after the exam to complain that the exam was too easy. And the professor was like, what are you saying? Are you complaining the exam was too easy? And I said, yes, the exam is too easy. How could you tell that I am a good student? Everyone will do well. And I was like so furious that the exam was easy. So, so my point is, again, I'm not bragging. It just is that I think a good exam should make the class spread out, right? Like you should appreciate a hard exam. You should, because it makes people show up. Like if you are a really good student, but it shouldn't be so hard that everyone gets a C. No. But what I'm saying is that if it's so easy that everyone gets an A, that sounds like music, right? Like, wow, it's so easy. That's a great class. No, it's not. A good exam should challenge you, should make people, spread out so that you can see who are the really good students that are going to be our leader for the future and who are okay students, right? Of course, the victim here is the people who are not ready at all for the exam, and a really hard exam like this can push them down. But the exam, a good exam shouldn't be like that. It should have some bar. So what I'm trying to say is that there will be like maybe one problem that is a little bit tricky, but there is still enough problems that take everyone to a safe B, right? So no C left behind. My expectation for a good exam is that majority get an A. Sorry, the majority get a B. But does everyone should get an A? No, only the people who are really good enough. Only the people who did sacrifice it. And I know that if I make my exam so easy that everyone gets an A, I will be the most popular professor ever. And everyone will write an evaluation. Amazing professor, very easy. But I'm not doing you a service. If I make the exam so easy that you cannot distinguish who did study and who just like reading from the solution manual and just like, ah, this is exactly like what we did. Tak, 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 tak. Okay. I'm not saying it's going to be hard. I'm just saying that you should appreciate, you know, when the exam is a little bit tricky.
I would agree if it was a little longer. I write slow and I think slow.
So the question is, you know, that's okay if you give us enough time, but if the exam is really short, you cannot expect us to spend a lot of time thinking. I do agree with this, and I am one of the amazingly. I remember that I finished an exam in my life. Okay, why? Because I really take my time reviewing the problem while I'm solving it. I always tell myself that if I finish quickly and then I will have the time to review at the end, that doesn't really help, because what if you screwed up the H1 in the thermodynamic problem? Like, then everything else is wrong because you're gonna get S1 wrong and S2 wrong. And so I always tell myself, no, it's worth slowing down while I'm solving, so that you because you don't have time to fix things. Like, you cannot build a car or a space shuttle and then figure out, we did something wrong, let's build it again. From the start, there should be like revision over revision over revision, and you don't move to the next step until you are comfortable. So every equation I write, I check for the units. Okay, so I just gave my graduate students an exam last week, and the equation was like for tracking a droplet evaporating, a fuel droplet evaporating, and they're trying to figure out. And the equation was saying d squared equal d naught squared plus lambda t. And one of the students asked, what is lambda is the evaporation rate in kilogram per second? And they didn't reply because he should have checked for. I said, I'm not going to reply to this question, because when the equation is this equal this plus this, then the units of the three terms should be the same, right? I mean, you cannot say the distance to Oklahoma City is the distance to Stillwater plus the time from Stillwater to Oklahoma City. No, it's distance plus distance. So any equation should have this plus this equal this, and they all have the same unit. So there are things like this, you know, when you check off the units of the equation you are using. When you check off the number, does the number square up at the end or not? When you put all those things, it slows you down, but it makes sure that the problem is basically in good shape. So back to your original question, which is, if the exam time is short, it should be pretty easy. So again, I'm one of those students that take forever when I was a student to finish, but I managed still to get good grades and graduated first in my class, because you do it perfectly and slowly better than do it quickly and wrong. But my point is, it wasn't good that I was slow. You should be fast. And if I'm a really good teacher, I should train you to be fast. Because if we are slow in rolling out our design, it will be worthless. Someone else somewhere in another country would have come up with that design and saturate the market. So from in your education, you should learn that I need to be accurate and I need to be fast too, right? So again, if I give you all the time in the world and you guys finish the exam half the time off, I will probably be super popular and like, wow, his exam is so easy and you can take forever, but that is not doing you service, right? So again, you know, the exam should be not to be done at 3 hours, but it should be just enough to be done in 1 hour for a fast student. Anyone that's slow probably will not finish and shouldn't finish, and should realize that he or she need to speed up the next time. And it comes with practice, right? So I'm trying to explain that you should appreciate if the exam is a little bit tricky and if it's a little bit a little bit long. Okay. So by the way, I really listen to the student evaluation every year. I read them very carefully, and I try every year. I'm saying this because actually we just got the email that they will start, that you can start evaluating the courses. And when you look at my courses year after year, they really change based on what the students say. So if the exam turned out to be really too long and everyone said, yes, the exam is too long, I probably will make it a little bit shorter next time, right? So I really listen, okay? And I have to listen because you guys are the experts in what make this course really, really good for the student next year. From like this side of the class, I could imagine things like, yeah, if I give them a quiz and homework every class, that will make them really learn. But maybe no, quizzes doesn't make you learn anything because you need time to go back home and comprehend the material and right? So I could envision things here, but only you sitting on this chair would really know for sure whether things are working or not. So not just in this course, but in all courses, you have to fill those reviews. And every year we struggle because students don't have the time to fill those reviews. But without the student feedback on the courses and tell us what did work that we should keep and what didn't work and it's waste of time and we have to change, the courses will not change and our status will remain the same. Just this, also this last week, we got an email from the dean about like the status of our ranking, the US news ranking, and some people don't care about the ranking, but it is important, right? And 30 years from now or 40 years, when you are really old person sitting with your grandchild on your in your living room and trying to convince him to OSU, it will make a lot of difference when you tell him, I want you to go to OSU like me because look, it's top 25. That's the reason why I joined in the first place. You know, I didn't go to OU because of this. It was a really good school. So the school will not get that high without you. And you are stuck with our name. We and you, we OSU and you, alumni of OSU, are married Catholic marriage. We will never get divorced because you will always carry our name on the top right corner of your resume. The first line will always say Bachelor of Science and then Oklahoma State University. So it's in your best interest for us to climb up in the rank. Okay, and we will never be able to climb up in the rank without continuous feedback from the students to make the courses look better year after year, and the students in this classroom get smarter and smarter every year so that they can get better jobs every year, and that's how we get higher in the rank when our graduates are evaluated higher and higher by the employee, right? So that's basically short answer for like what is my philosophy for the exams. I think they are there for a purpose, not just to hand grades. Otherwise, our degree will worth nothing. We become a diploma mill. Here, give me $5,000, here's your diploma. $5,000, here's your diploma. It shouldn't be like this, right? The harder, not the harder the exam, but the more valuable the courses, the more people will evaluate your degree and like, oh, you're a graduate from OSU. Not you're a graduate from a small university somewhere in the middle of nowhere, right? Again, I'm not saying that's an excuse to make the exams unsolvable and extremely long. I'm just saying a little bit of a challenge is not a bad thing. Okay, that's all I'm saying. And if I went too far, you will let me know, and it's an easy fix, right? I mean, we can always just make one problem extra or something, right? So I think if one student touched the top or near the top, then I'm fine. Then basically I get the exam really right. So that's how. So we can revisit how difficult the exam is after we grade. All right. So now the next section we'll talk about the homework at the end, but I just wanted so that we don't waste any more time. Let's go into the next part of our course. The next part is heat transfer. Okay. And so last year in the evaluation, one of the students wrote how this course is horrible because we had to use 3 textbooks. That was the complaint. Why are you using 3 textbooks? That is not really something that I can change. Why? Because it's like when you graduate and you work on say a power plant, or you work in an oil rig, and they tell you, well, can you calculate for us how much is cooling of that mechanical vapor commission cycle? And you say, yeah, I know how to do this. I know this in the dynamics part. And can you also calculate the pressure loss in the pipe? No, I cannot do fluid mechanics. I can only do, you cannot ask me to do two things. They will fire you. You as an engineer have to learn how to do different things. And in thermofluid, those three things are fluid mechanics, thermodynamics, and heat transfer, right? And that's the same what will happen to you in next year in your capstone. So in the capstone, you cannot tell the company that you're trying to solve them the problem, I'm going to calculate for you the failures, the shear stress that will break your test thread or your jet engine holder, but I'm not going to do the fluid mechanics part. I'm not going to calculate or the heat transfer. You can't, right? So what I'm trying to say is that to be able to design a thermofluid system, we need to learn those three things: thermodynamic, heat transfer, and fluid mechanics. So as much I would love that I just teach one topic and we go in depth, this course is different. This course is trying to teach us how to handle a thermofluid system with its three components, right? But the good news is that I'm not asking you to get a new heat transfer textbook. It's the notes that it's uploaded here. This is this part. This is exactly from our heat transfer book that we use in this college, right? Like who had his heat transfer course last spring? Raise your hand. 2, 3 people, 4 people. Who had heat transfer a year ago, not this year? Okay, 2 more. Who had it like 3 years or older before? Long time ago. 1 person. All right, so you probably still have the textbook. I mean, it hasn't been that long, right? And if you don't have the textbook, don't worry. The material of this chapter is good enough for me. But a good news also, again, we are not buying a new textbook or anything. There is this 2 professors at MIT, and they write an excellent heat transfer book and they put it online. And if you just click here, you can download the whole book. Okay, it's an excellent book, but we only need chapter 3, which is heat exchanger design. And on top of that, on top of the actual textbook, they have the solution of all the 43 problems in their chapter 3. So the heat exchanger chapter, which is chapter 3 in their book, and all the solution of those 43 problems are uploaded for you, right? So between this and between the PowerPoint, which is mainly Dr. Gajar book, you know, the one, that's the book that you got in heat transfer, right? By Dr. Afshin Gajar, correct? Between those 3 things, we are in good shape. You don't really need any heat transfer book. Does this make sense? Yes. So let's start with the introduction to heat transfer. Okay. So, and that would be chapter 1 and 2 in this chapter 1 and 2 in the MIT book, and basically the first 9 chapters in the heat transfer book. So the whole 9 chapter in the heat transfer book is really introduction for how to pick a heat exchanger. Okay. So in thermodynamics, what we learn is the energy balance, the joules. So if we have like a piece of ice sitting in that room, and the room is hot, the ice will melt. Why? Because he gets Q, right? You get energy from the air into the ice, and that is enough to turn the ice from solid to liquid. He will melt. So thermodynamics will tell you that the joule that you're getting from the air should be equal to the joules that the ice took to melt. So the mass times the latent heat of melting will be equal to the joule that you are getting from the air. But thermodynamics doesn't tell you how long will that piece of ice stay in the counter. Will it melt in 1 minute or 1 hour or 1 second? That is the role of heat transfer. So the heat transfer basically tell us the rate, the joule per second. How quickly will that energy move? Okay. So the three mechanisms that heat move by is conduction, convection, and radiation. Right? And in heat exchangers, the radiation basically is not that important. Right? So radiation usually happen at very high temperature, like in flames or things that, or sun. All the energy that we get from the earth, from the sun, is by radiation. Right? But the sun is at what, 5,000 almost Kelvin? So hot. That's why radiation is a big deal. And every one of you radiating, by the way, right? But you are radiating in the infrared. As long as you are above 0 Kelvin, we are all above 0 Kelvin, you will radiate. But the wavelengths at which you radiate is really function of your temperature. So hot, very, very hot things radiate in the visible light. That's why we can see the sun. But when you are not that hot, you radiate in the infrared spectrum, right? So that's why if I put my infrared Google, and I look at you and we turn off the light, every one of you will be so bright in the infrared, right? But in daylight or like in the visible spectrum, you don't show up because your temperature is not that high. So anyway, so we will ignore radiation a little bit and we will focus on conduction and convection. Right. So in conduction, if you remember, there were so many chapters in the heat transfer book about conduction. Why there were so many chapters? You remember what was the title of those chapters? There was at least 3 chapters. This is just like the basic fundamental thing, and then when you start having unsteady, right? When things are not steady state, but the temperature is rising, or like you put things in hot water or you put things in cold, pass, and then how does the temperature creep in by conduction? Like if the ground is start to freeze, how quickly will the temperature go into the ground? Like how long before your pipes start that spiral down? How long before it freezes? All those are conduction problems, right? And so it basically followed the Fourier law, which basically say that the heat flux is function of the temperature gradient. So it's delta T over L, right? That's the Fourier law. And then when the wall is flat, there is one form. When the wall is a cylindrical, like cylinder pipe, it's another. When it's spherical, like spherical shell tank, this is another one. Okay. So the bottom line is basically for conduction is Fourier law, and it's the Q dot, the joule per second, is minus Ka partial T partial X. And why the minus? Anyone? Why Fourier law has a minus sign? Help. So Q dot is minus K, right? A partial T partial X. What does this minus signify? Can K become negative? Anyone? Can K become negative or it's always positive? Conductivity, K is conductivity. Always positive. And the area is always positive. So the Q, can the Q be positive or negative or both? Yeah, it depends on the direction. If it's If it's leaving the control volume, it's negative. When you are adding, it's positive, right? So Q dot can be plus or minus. And so obviously the sign of Q dot depend on the sign of partial T, partial X. And that minus tell you that they are opposite to each other. So when the gradient is positive, what does a partial T, partial X that's positive look like? If I'm moving in the X direction, T should increase or decrease? Increase. That's what partial T, partial X being positive mean. And so if something is like this in a wall, where the temperature is getting hotter as we are going with X, maybe because inside is the flame or inside is the boiler or the furnace, and we are designing the wall, they are telling you how thick should be the wall of our furnace. So the heat will move from obviously from the hot to the cold. The Q should be like this. So the Q dot direction is negative with the X, while the partial T, partial X is positive with the X. So that's the meaning of the minus sign, right? That the temperature gradient is opposite to the direction of the Q. Make sense? And so then he will integrate this to get the temperature distribution. Okay. And because it's basically those are not function of distance, the integration becomes so easy, and the equation become minus K T minus T over L. Okay. So this should remind you of. So we are saying that then this in a flat wall like this will end up being T, let's call this say T1, and this is T2. It will be T2 minus T1 divided by the L over KA. So I took the KA and I put it over there. So this equation should look similar to a famous equation in electricity that basically say I is V over R, where V is the voltage, that's the power, that's the potential, that's what drives the current. And R is the resistance to the current. The higher the resistance, the smaller the current. The smaller the resistance, the bigger the current. So our Q dot is like the ampere, the current. And their voltage is basically our temperature difference. And our R is this. So it's as if for conduction, there is a resistance for the heat to go through. What is that resistance? L over KA. Makes sense. If L is big, long pass, that is good insulation. That's big resistance. That will give you small Q, right? And how about K? If K is small, like you put fiberglass, or in old time, we used to put asbestos until we found that it gives cancer. For small K, that is big resistance. Yeah, makes sense. If the conductivity is small, the heat will not move. So this is really our R. Okay. So the heat transfer by conduction is simply now Q is the temperature difference, T2 minus T1, divided by R conduction. What's our conduction? That is basically your L over Ka. Okay, so that is pretty easy, right? That is what's shown here in this slide. So L is voltage over R, same thing. Q is delta T over R. Okay, and what's our R? It's L over K. Good. So now if this was not a flat plate but a cylinder, the Fourier law still hold, right? The Q dot, the unit area, is minus K partial T partial R this time. In cylindrical coordinates, it's not R, it's R. Okay, and if you want the actual Q, you will say minus Ka partial T partial R. And of course, what is the area for heat transfer? If this was a long cylinder and the cylinder is inside, you know, sitting at T1, hot oil or something, and outside is T2, what would be the area for heat transfer? What is that area? Is it pi over 4 d squared minus d squared? D out minus dn? Is that the area for heat transfer? Is this the area for heat transfer? No, it's not. The heat transfer happened like this, happened along the length of the pipe, happened along this. That's the area for heat transfer, especially if the pipe is really long. The end doesn't even matter. It's mainly the, so it's basically that area should be 2 pi RL. Circumference, length. So then if you write K 2 by RL, then this L, this R over here and partial T partial R complicate the integration a little bit to get the Q. So it will be, you're gonna integrate dr over R. What's the integration of dr over R? What's the integration of dx over x? Anyone? Yes, len. It will be len x, right? And you're gonna, or len R, then since we're doing R. It's gonna be len R. And it's from R1 to R2, so you will end up with len R1 minus len R2. And you remember len minus len is actually len R over R. Right? So then it makes sense that you will end up with, fortunately, the same format. Q is still delta T over R. That's what's nice about conduction. Plane wall, cylindrical wall, spherical wall, it's always delta T over a resistance. But the resistance shape change. So for cylindrical, it's len R2 over R1 divided by 2 by L K. That is the resistance of a cylindrical shell, right? You know, it's like the foam that we buy for our HVAC duct, not HVAC duct, HVAC pipe, leaving your house, going into the outside unit, there is pipes. And this pipe, you have to seal it, right? You buy those foam things from Lowe's and you seal it. And then what we put at the end, I didn't do the last time. And after it lasted like 5 years or something. And then the pipes start to, the foam start to die basically, or like break. Why? What is the part that I didn't do? I was taking care of the conduction, but I didn't take care of what else do you recommend that you should put on in your pipe beside that foam thing? What else you need to do? The shiny, right? The shiny tape. The shiny tape, right? Why? Because you are trying to get rid of excellent radiation. Because in that shiny metallic tape that you put will reflect the ultraviolet radiation from the sun. Everything coming from the sun will go away. But you just put the black foam by itself, and he will absorb all the radiation. Yes, hopefully he will work as insulator, but he himself will get hot. And that is not good year after year, right? So I got them in my car. I got the shiny part, so I can, if I find the time, I will seal it. Nice. Okay, so cylindrical conduction, Q is delta T over R. What is R? Len R2 over R1 over 2 by LK. Okay, good. So I'm not showing the spherical, but you can go to your heat transfer book or just look at that book that I uploaded for you, and you can see what is the resistance for a spherical tank or a spherical shell. And you may think like, who cares about spherical? Like who would make a spherical? But they do in natural gas, right? When they are like those cars, not cars, those ships that take liquefied natural gas, they usually, the ship will have them in spherical tanks. Also like high pressure tanks, sometimes it's like much easier to build them in spherical shape because they take like a lot of pressure compared to cylindrical. But anyway, let's take to heat exchanger. Therefore, we care about cylindrical geometry, right? So now convection is, what is conduction? Conduction was, you are molecule vibrating, I am next to you. When you vibrate like this, I vibrate next to you. And how much I will vibrate compared to you will depend on the R between us. Okay, so conduction require contact. The molecule need to be sitting next to each other. Convection is basically when the fluid transferring the heat is free to move, right? When you put like something hot on a surface, you put a piece of metal like this, well, guess what happened to the air next to it? It will get hot and he will leave. And when he leaves, he will bring new cold air instead of him. And so that room will basically have a current like this that will keep changing the air on your hot piece sitting over here. That's called natural convection. Convection is happening because of buoyancy. Air is lighter when you get hot, so he moves. That happens also in liquid. Okay, natural convection. But you know, when you are like waiting for your fries to cool down to eat them, and they are pretty hot and you cannot wait and you have to leave, what do? Like the fry does not want to get cold. You do this, right? So you're turning natural convection to forced convection. So that is basically as if you are putting a fan, and that's why, because why you're doing this, because the rate by which things are moving are still slow. You want to be completely covering that piece of metal that you are trying to cool by always fresh charge. You cannot wait for it to, you don't want the air to get hot, and because when the air gets hot next to it, he prevents more cooling, right? Because if the air next to the piece is hot, why would the piece move heat to him? But if you put cold air always, all the time, next to that piece of metal, it will always send the heat transfer out, right? So this would be forced convection, right? And there is natural convection, and sometimes we use both of them. So where do we use natural convection in our house for cooling? In our big flat TV. Okay, if you open your flat TV, you will see that at the back they have a heat sink, and that heat sink basically have fins like this. Okay, and so those fins basically, and of course they should be vertical or horizontal, those fins. Vertical, excellent. So that the air have a chance to get hot and leave. I mean, if they are horizontal, then they will trap the air in the middle, right? But it's basically continuously cooling you. And why it's natural convection? Because you want it to be quiet and pleasant experience watching the TV. But the Xbox, is it natural convection or forced convection? Forced convection, right? Because I mean, it's like so much energy and you cannot wait. So they just basically have to very good. So we need to, of course, the convection happened or the heat transfer happened because it's still the same thing. You got a hot surface and hopefully a cold ambient. And the difference between those two guys make the heat happen. So the Q dot is proportional to Ts minus T infinity. Okay, and of course it would be the area. So let's put the Q dot, not the specific one. So the joule per second, not the joule per second per meter square. And the constant of proportionality will depend on how easy the air is moving through those things. So it depends on the geometry, it depends on the speed. Is he moving quickly, slowly, right? What kind of fluid he is? Does he have like big CP? He can take a lot of joules on him, or he pretty much you throw 2 joules on him and his temperature rise so much. So all those things we lump it down into something called H, heat transfer coefficient. So writing this equation doesn't mean we know the heat transfer. Actually, we don't. Unlike the conduction, when we say Q dot by conduction is minus Ka partial T partial X, we got it. We know the K, we know the area, we know the temperature gradient. But when we write the convection like this is like rephrasing the question. Basically, you're saying we will know it, we will know the Q. I mean, the question was, what is the Q? Now we just said, well, what is the H? And there are, bunch of equations that will give you that H in terms of the speed of the air and the mechanism. I mean, is it natural convection or forced convection? Forced convection on a pipe, or forced convection inside the pipe. Okay, so that's why there's like maybe 3 chapters in convection in the heat transfer book, maybe 4 chapters, maybe 1 introduction and 1 was internal. I didn't teach heat transfer since 2014, so that's why I don't really remember that. But I remember chapter 10, which is what we are here for. So there is like chapter on internal convection, chapter on external forced convection, so internal forced convection, external forced convection, and a chapter on natural convection, right? And in the end of the chapter of natural convection, they tell you the part about, so should we consider natural convection if it's sitting in with forced convection or not? Like an example like this, where you have like a fan, disk fan, and you have, like an electronics or something, do you calculate the heat transfer just by forced convection, or do you also want to consider this part? And it's simply calculating the ratio and figure out whether it's like Bill Gates and Dr. Salam, or it's like, no, it's Dr. Guy and Dr. Guy. And so they have the same value of force, right? So it basically allows you to estimate that H against this H before you start. You'll be able to base your, where should I put my calculation? All right. So again, convection is all about this H. QH convection is the holy grail of convection, how we can calculate that H. Okay. And there are graduate students that, like spend their life, 4 years of their life for the PhD. I have one right now working on heat transfer on convection, like convection heat transfer coefficient for a new kind of boiling. When we are trying to make the boiling from the floor so efficient. So he's trying to calculate what this new H. So he's building the experimental setup so that he can measure that H. So then he can put it in a graph, and then that graph will generate a formula. Then that formula will be used by people using that configuration. So whenever you're using this configuration, we'll use that equation for the H. So there are so many H for so many configuration, right? Done by so many people, right? And in general, the H for water flow is so high, but the H for airflow is so low. The air is not good in moving convection. Okay, so how we can help the Q to get higher? Fins, right? So what does the fins do? It will increase your area S. Okay, so when the pipe is basically this much or this surface, but then you bring so many areas. That's basically how you can get your Q to be high. Make sense? So the shape of the fence and the orientation should be in a way that is allowing the air to go through, and two, they wouldn't compete with each other, right? And three, they should be efficient surface area, meaning that if I have a like a wall, say a chip like this, on a motherboard or some electronics, should I make my fence that tall, or should I, instead of having this like that, I should actually make a few shorter one long one with the same area, or 4 shorter one with the same area? What would be a better design? Yeah, because that guy, when he's far away, like here at the floor, he's probably having the same TS near here. But as he starts getting away and get cooled by the air, he will become colder to the extent that this part would be as if it's sitting at T-infinity. The farther away you are from the wall, the cooler you are. And so what? So then all this area is useless. I mean, what is the point of having a surface at the same temperature as the air? You want surface that is at the same area or the same temperature like the surface, right? So that you really increase the surface area, right? And so that's why in the equation with fence, when they add the fence area, they usually multiply by efficiency. So it will be the area of the surface plus not all the area of the fence and efficiency of it. And the taller the fan, the less this efficiency. Not all the surface is basically engaging in reasonable heat transfer, right? Very good. So chapter 3 was in the heat transfer book by Dr. Gajar. We are reviewing basically the heat transfer chapters that we had in our 32, 33, right? Heat transfer, ME 32, 33. So chapter 3 was multi-layer. What was multi-layer? Sometimes it's like one layer moving to another, like the envelope of our buildings, you know, you got the brick, you got the insulation, you got the stone wall on the outside. So what you do is that, well, if they are in series, we just add them, R plus R. And when they are in parallel, we add them with what? 1 over R plus 1 over R. That would be 1 over R total. So when they are, and how is the temperature in series? The flux need to go from this one to this one to this one. When they are parallel, that means that the flux can split through them, right? So here is the example of things that are in series. 1, 2, 3. And notice that the 1 and 3 is actually convection. The heat transfer by convection is one of those resistance, like the air is convecting to the wall, and then the wall has internal conduction or conduction inside, and then convection. So when you add those, because they are all in series, it's basically that R1 plus R2 plus R3. R convection plus R wall plus R convection, right? And we talked about R conduction before, right? And we said it was R over KA, okay? How did he do this? Because he said the Q dot was KA T minus T over L. So when you bring this and you put it down there, this becomes your R. So similarly, that's what you can do with the convection. What is Q convection? H A T, say infinity minus TS. depending on which one is hotter. So you can take this guy down there. How down there? You put it as 1 over HA. This become your R convection. So our conduction R L over Ka and our convection is HA. Okay. Make sense? So you can see 1 over HA, that's convection, 1 over HA, that's convection, and L plus Ka, that's conduction. And this is adding the 3 of them together. Right? Questions? Okay, and for a cylinder, you still can have convection in the inside and convection on the outside. That's internal force of convection, and outside could be external force convection or external natural convection on the outside. Like if the pipe is left basically without air on it, just buoyancy and stuff. Right? So you add 1 plus 2 plus 3, right? So here is, this is 1 over HA. Notice that the area of the cylinder, that's a common mistake. We will always think, well, pi over 40 squared. No, it's not. It's a cylinder. The area is 2 by R L. That is the area for the heat transfer. 2 by R, right? L. Okay, and we talked about cylinder conduction. Then R2 over R1 over 2 by LK. Okay. And then chapter 4, that was the unsteady heat transfer by conduction. And so what did we call this equation? Does anyone remember? We used to call it the general equation of conduction, but when you look to it, it's really nothing but the first law of thermodynamics, but like written for conduction. So what would be the first law of thermodynamics? Q minus W equal, right? M dot delta H, right? That's what this exam today is about, by the way. First law of thermodynamics, Q minus W equal M dot delta H. As a matter of fact, if there is any problem that look weird for you, just try it, M dot delta H, and then assign it to something, Q or W. Everything is M dot delta H in the first law, right? So, but in conduction, there is no M dot. Nothing is really moving. So it's really Q dot minus W dot equal to the unsteady term. The unsteady term, which is partial T, energy inside. That is the unsteady term. And that this is really the Q dot. So what is the Q dot? Q dot coming by conduction according to Freire law, and if there is inside heat generation, if there is, maybe that's an electric wire and you generate heat from inside, okay, that make him hotter. Or maybe it's a nuclear fuel rod and there's nuclear reaction happening inside, right? So in nuclear fuel rods, they will be like this, and inside there are the uranium-235, and then it's surrounded by water everywhere, swimming in water basically. And so there is radiation there is fusion that happens inside, and that generates E dot inside, watt per meter cube, right? And then you are basically trying to cool it from the outside. So that is a scenario where this E dot inside will actually exist. Inside the rod itself, inside the thing that you're studying, it's heat transfer, he's generating his own heat. Okay. And so the purpose behind that chapter was to calculate the partial T, the temperature change with time. And so basically this equation say that if you give me heat transfer, I'm gonna take my temperature and go up. like this, like a bunch of water sitting in a pot and you are heating, you are sending radiation, or sorry, sending Q by conduction to the wall, to them, right? And if that energy is coming not by conduction but by convection, fine. The Q dot again is the first law. You say Q dot minus W dot equal to the change in energy inside the control volume. So there is no work, but the Q that's coming could also come by heat transfer, HA delta T. Like food, you take it out and you put it, and he's basically getting heat from the room. Or food you are putting inside the fridge and or the freezer, trying to figure out how quickly before he will solidify. That would be something like this. Okay. And so there were charts basically that will solve those things when you make an ideal geometry. Like you would say, well, I'm gonna simulate this as a perfect sphere or a perfect cylinder or a perfect slab, and then you'll be able to check how quickly will it take to for the temperature inside to drop. You remember those charts that have the point number in it? And it basically you'll be able to track with time how quickly will the temperature move. So fortunately, we will deal with steady state in this course. So, but it's nice to remember that there was, how did we do the unsteady part? So again, the radiation really makes sense, or it's very important when temperature is really high, like flames. You know, when you are studying the radiation from a flame or a fire camp or a fire accident, if there is a fire in the corner, the fire will actually move to the whole auditorium, not by convection of the hot air and coming, but just by radiation. Like if the fire is at the corner, that bench will catch fire just because he sees the fire in front of him. So that is a very, especially if the flame is shooting, like he's making that black particles, those radiate like crazy. They are very, very good emitter of radiation. So a shooting flame will be able to send the energy to different places rather than just waiting for the convection to go up and make the ceiling so hot and then the ceiling will catch fire. There are people that really work on just investigating accidents, fire accidents for insurance. So like we go to the place and they can see where is the place that fire started and when and how. So the mechanism for radiation is basically, or the way to model the radiation is this equation, which is sigma A T to the power 4 minus T to the power 4. That's why when the temperature go up, T to the power 4 becomes so big, and then the radiation dominates. Right? And sigma, that is the Stephen Boltzmann constant, the best constant in the whole universe. Why sigma is the best constant in the whole universe? Anyone know why? Stephen Boltzmann constant is the best constant ever. Why? Because it's 5.67 10 to the power minus 8. It can never get better than this. 5, 6, 7, 8. Right? Like you cannot forget it even if you want. How could you remember and forget a number like this? 5, 6, 7, 8. So, and what is with epsilon sitting over here? That is, you radiate with sigma to T to the power 4 if you are a black body, but we are not black body, we are gray bodies, and so because of this, we are radiating with a ratio of that black body radiation. So the epsilon is our basically emissivity, how far you are from perfect radiating black body. Okay. Very good. So I think it's a good time to stop right now. So let's stop for 15 minutes break. And when we come back, we will look at the next part. 10 minutes break.
You say 10 or 15, sir?
15, sorry. We start 45. Right, I think it start. So people online, can you confirm you can hear me? Yes, all right. So as we said, you know, the whole heat transfer course was about finding, you know, the resistance really for heat transfer. That's basically say prevent the flow or control the heat transfer from a hot fluid inside to the ambient, or the water, seawater outside. Maybe this is a crude oil pipeline going under the Gulf of Mexico or something, or a natural or a steam plant pipeline taking the steam from one place to the other. So it was all about this Q dot, which is T1 minus T2, T1 being temperature here, T2 being temperature here, over a bunch of R's, like 1 over HA plus ln R2 over R1 over 2 pi KL plus 1 over HA, right? Bunch of resistance. Or we can actually just simply say T1 over T2 over the whole big resistance. Huh? Let's call it 1 over UA. What's 1 over UA? Just like H was the heat transfer by convection, U is the overall heat transfer coefficient. Overall. So you just multiply this by saying the area out, and that will be U out. And so now Q dot is U naught, area naught, T1 minus T2. Area naught being the outside pipe area, and U naught over is the overall heat transfer coefficient. So this is the equation of the heat transfer book. If there is one equation that you need to remember, it was this. Okay, this equation is really important because it tells us when we are designing the cycle, whether it's mechanical vapor compression or Rankine cycle, Watt cycle, is that you need a certain temperature gradient. And if that temperature gradient is small enough, or it's too small, then you have to compensate this with a really big area, right? But if you make the temperature difference big, then the area for heat transfer doesn't have to be that big for the same Q dot. So you make the fluid that is, so I have a friend that worked for making HVAC system for buses, big commercial buses. And so the customer would tell me that the customer would come and say, design the system for a delta T of 2 degrees. And he will tell them like, why? I mean, this will have to make a huge heat exchanger for it. And you guys don't really have only two temperature or 2 degree temperature difference. You can afford to make it a little bit bigger. So then the design will be common, but they are trying to oversize the system so that their Q is really big even with a very small temperature difference, right? But that is the significance of this equation. And of course, one could say, but it's not just T and area in the equation, there is also U. And yes, people try to help the U, try to make it bigger by making the water move faster, by trying to make the water become turbulent. Okay, so inside the pipe, they have something called, it's coming from turbulence, turbulator. So they put all those X's, and if you come to my office upstairs, you will see those things inserts that they put inside the pipe, so that the water or the fluid will basically have to go like this in the pipe. So he will hit the wall back and forth. That help the U. They also make heat exchanger that look like this. That the heat, the pipe or the plates for the fluid, hot fluid, is already corrugated. Why? So the fluid hit the wall, hit the wall, hit the wall. So all this is trying to improve your U. Huh? But really, at the end of the day, I mean, people use the best U that is, there's nothing in your head to change the U. I mean, you're going to use just the best state of the art U, but it's really the area and the delta T that carry the day. Okay? And I know at least 3 students that work in heat transfer. After they graduated from here, they work for a heat transfer company in Tulsa that they make like huge heat exchanger for a lot of countries. And their life now, since they graduated, we took some students and visited them a few years ago, and that's where I met them. Their life is basically this equation. That's their career now. It's just like this equation. But of course, how to get the U, right? How to make the right type, we will see what's the type of the heat exchangers. But this equation could be the career of some of you. For example, if you end up working, and we in Tulsa, we are really lucky. We had a lot of companies that just make heat exchangers for different applications. So heat exchanger. Again, Q dot is UA delta T. The problem about this in this course is all about basically sizing, like what area do I need, or calculating the Q dot that will come from it. Okay, so either you know the Q and is asking you for the area, or you know the area and you know the condition and you're asking you, well, so how much heat transfer will I be able to get? So it's pretty easy when you think about it. There are 2 ways to calculate this equation. One of them is called the logarithmic mean temperature difference method. What is that? Does anyone remember from his heat transfer course? What's the LMTD, logarithmic mean temperature difference? What was this about? The essence of that method was about what? Anyone? Anyone remember what is the logarithmic mean temperature difference? No? So this was about the delta T. The delta T, you would think the delta T is easy to calculate, it means T hot minus T cold. What are you talking about? Well, no, it's not that easy because even for something like this, when a flow is going, say hot fluid going into a pipe, and there is air outside, that's not going to change. There's tons of air outside. So it's T infinity. If you plot the T infinity, it's like this. I'm plotting it as, say, as function of X, as we are moving with X. But the fluid is doing that. I mean, he starts with T in and he leaves with T out. And he's getting colder as he's going into this pipe. And so that you now see the question, the problem, right? The problem is, which delta T should I use? Should I use Ti minus T infinity or T out minus T infinity? Which one we should use? When I'm using it for this equation, the Q dot is UA delta T. Delta T between what? Between the hot guy and the cold guy over here that's trying to cool him. Which one should I use? Use the average, kind of, right? Use the average, so it's like kind of, well, the average temperature would be this. And that would be the T average, which is T plus T over 2 minus this, right? This is actually good approximation if the temperature between this and this is small. But if the difference is big, long pipe or something, then the whole method of logarithmic mean temperature difference is to figure out what is a good delta T, right? What is a good delta T? And that was basically, so the whole thing is about calculating the delta T. The second method, which, you know, I personally, when I was a student taking a heat transfer course, I used to be scared of that method. It just like the equation was so big and it make you really scary, make you scared, but it's not. It's actually very, very easy. And if the equation is complicated, so what? I mean, we are not going to use the equation. There is a MATLAB file that will use the equation for us. We just have to tell him what kind of exchanger, go for it. But we are not really gonna use the actual formula ourselves. There's also charts for it. And you can just read from the chart. So don't be like me, don't let the complexity of the equation and they have exponent and stuff, and don't let that scare you. So that method is called, the second method is called, anyone? Effectiveness method. And it's all about this parameter called epsilon. And that epsilon is the relation between the Q actual in your heat exchanger to the Q dot max. Epsilon is the effectiveness of the heat exchanger. If that heat exchanger is very effective, if it has the effectiveness of 1, then he made the dream happen. What's the dream? You get Q dot max. And when you think about what is the dream, think about heat exchanger like this, where TC in, and this is TC out, and this is, I guess, T hot in, and this is T hot out. So the hot is doing this while the cold is doing this. Okay, and of course the dream is, if you are designing a heat exchanger, the dream is to take that hot fluid coming in and you cool him down all the way to TCN, right? Or the other way, take that cold fluid and heat him up all the way to the inlet hot fluid. Or basically doing what? This is called Tmax. That's the largest temperature exists in that heat exchanger. Difference between two T hot N and TCN. If you manage to make one of those guys, one of those hot or cold fluid, go to that big delta T, the maximum delta T, you are 100% effective. The heat exchanger can never ask for more than this. Okay? It's like his GB is 4 out of 4. I mean, what else could you ask him to do? He took the cold fluid and take him all the way up to T hot N, right? And so the equation, basic, of course, again, don't get me wrong. We are still in the whole idea behind this calculation is get Q dot max or calculate the area. Okay, and although this equation doesn't show where is the area, but the area is embedded inside this effectiveness. So that effectiveness has a lot of formulas, and that effectiveness is function of UA over M dot CP. So if you know the effectiveness, you know the area, right? So both methods yield the same thing. Either give you the area if you know the Q, or give you the Q if you know the area. Right? Just like we will see why we would prefer one over the other for certain problems. Okay, so logarithmic between temperature difference and effectiveness. So again, I'm doing this all from the heat exchanger chapter 11 from Dr. Gajar book, the one that you guys used in the heat transfer book. But that textbook that I already pointed out to here, the free book from MIT, download the heat transfer book, and those 42 solved problems in heat exchanger are perfect. Those are all what you need to understand heat exchanger design. Okay, so you download those two guys if you don't have the book. Okay, and if you do have the book, then we are in good shape. All right, so the objective is to basically figure out the performance of a heat exchanger, figuring out his Q dot actual, basically, or his area. So now there are two configurations, two fundamental configurations. And one of them is called parallel flow, where flow comes from one side and leave together, parallel flow. And then there is counter flow. And it's very clear which one is better with relation to achieving the dream. What's the dream? Get the cold fluid all the way up to T hot N, or get the T hot N all the way to TCN. Basically, make one of those two guys get delta T max on him. Which one is doing this? The counter flow. So counter flow would be ideal compared to ideal flow, which is putting a cap on each other dream. Basically, they have to meet kind of in the middle, kind of. Right? So of course, we would prefer counter flow, and we would always try to be, if not pure counter flow because of size limitation or geometry, then we will try to be as much as possible to be in counter flow configuration. Okay. And from thermodynamics point of view, I mean, what I said, that's just like the layman explanation why we like counter flow compared to barrel flow. But from thermodynamics, why barrel flow is horrible? Because this is not good with second law of thermodynamics. The entropy will jump like crazy when you give him delta Q over big delta T. If you have very hot heating, very cold, that is huge source for entropy, right? You don't want to do this. You always want to maintain small delta T across the heat transfer. Okay, so thermo love that. Thermo love very small delta T. Heat transfer doesn't like that, or at least will make you pay for it. If you have small delta T, then the heat transfer will make you pay more area, right? But thermo basically would love this. The efficiency would really improve. How would the efficiency improve? Because that temperature, if you take it up, that you are increasing the exergy of the fluid. You are adding energy at high temperature. So he's like really more valuable. You can get stuff from him rather than giving him the 100 joule at low temperature when he's like sitting here. Okay, this is bad, this is good. When you are delivering energy at high temperature for him, he now can do a lot of great things. You're launching him into the next process with more value. With the same 100 joule, but at high temperature is much better than 100 joule at low temperature. All right? So this is a very common geometry, right? Shell and tube. And you can see how the steam is going in the, like, or whatever the fluid here is in the shell type. And then the other fluid is moving in the tube. So this is the shell side and this is the tube side. Okay. So you would love to have counter flow in a configuration like this. So that's why if you have a choice, you will send this guy this way while the other one will go this way. So this way they will be in almost counter flow. Okay. And so there is also the choices of which fluid should be in which side. So usually the dirty fluid should be in the pipe side because it's easier to clean the inside of the pipe. You can just like send things, brushes and stuff and clean the tubes, right? But clean from the outside, especially if it's like a bundle of tube, how could you reach and clean? You can. Also, when it comes to condensation, if you're gonna condense steam, like steam is coming, you know, in the TS diagram, how we send the steam like this, and then he condense and become liquid while doing what? While heating the other fluid from, say, here to here. This is the TS diagram. So if you are going to condense steam and he's going to make like droplets, sorry, HF, he's going to make droplets, then it's much easier to condense on a tube rather than inside tube. Especially if it's, I mean, imagine if it's condensing in a horizontal tube, how is that going to work? Like, will that block the rest of the flow, or will we start having bubbles now inside the liquid? Because it's going to be horrible. But condensing and let the droplets form on the tube and then fall down, that sounds like a good plumbing technique. You know, just let them rain on the pipes, and basically they will drip from the floor. And you see how he slopped the floor so that the water can collect rather than sit here in the corner, right? Of course, the arrangement of those tubes. I mean, if we look at here and we say how they are sitting, probably this configuration will be favorable than this configuration, right? If you set them like this, that's not a good idea. But if you let them get staggered like this, that is a good idea. Why? Because if we set them in rows, the flow condensing on the top one will drip, right, on the other one, and it will basically isolate the guy at the bottom from the rest of the steam. It will be covered by a blanket, right? So you want to stagger the pipes so that they have a chance to freeze steam. You want them to be able to reach, the steam need to be able to reach them, right? So this is like one through, huh? The pipe side just go from one side to the other. But sometimes you don't have the luxury or the plumbing to go from one place and leave from the other. Maybe you really have to go and come back from the same side of the wall, just because of the space. Okay, so then that shell and tube side could have configuration like this. You could have one shell and two tube pass. So that's called two tube pass. One shell pass and two tube. So the shell side go once and leave, but the tube go back and forth. And you can have it like this, 2 shell and 4 tube pass. So it's important to be able to distinguish between those things, because there are charts for calculating the logarithmic mean temperature difference or calculating the effectiveness, depending on which method you can use. And those charts depend on, you have 1 shell and 2 tube, or you have 2 shell and 4 tube, or you have 3 shell and 6 tube, or you have 4 shell. So you need to be able to distinguish which one is it in the drawing. All right. This geometry here should remind you of your car radiator, right? So this is what cross flow heat exchanger. So the cross flow heat exchanger are not great from heat transfer, but it's really life saver when it comes to space. It's very compact, right? But why it's not really that great? So I define great as being counterflow. Anything close to counterflow, that is great, because you can really dream of getting that delta T max. But when you are in cross flow, what is the problem? The delta T between the air and the fluid, right? Or basically the fact that, you know, when you come here, inlet, you are meeting the inlet. That's like barrel flow. This area of the heat exchanger is kind of like really horrible. I mean, this area is good. Actually, I mean this would be much even better. But you can see how the exit is meeting the inlet. The exit of the tube is meeting the inlet of the outer tube. So that is good. That's kind of counterflow. But when the inlet meet the inlet, he will immediately get cold, or like at least lose heat transfer from a big delta T. And that's not a great idea. But you can see how they managed to put a lot of space, a lot of surface area into a very tiny location, right? And so the radiators are like this, basically, because you don't have that much space and you have to send all the air into the tube in a very small place in front of your engine, basically. Right? So there is for the chart of cross flow, you have to tell whether it's mixed or unmixed. And mixed or unmixed is the flow is divided into small channels, small passes, then it's basically unmixed, like this. The tube side here is unmixed. Every part of the fluid is moving in its own pipe. But the air is mixed. Let's all go together, right? So again, you will use the right chart depending on the geometry, right? And there are certain configuration that will look a little bit weird, and you really have to think carefully how you're gonna handle this. So for example, this wheel, rotating wheel, sometimes they call it enthalpy wheel. Okay, how does it work? This is happening in big HVAC system. It also happens in every big power plant. Before the flow leaves the chimney, the last thing that he see before he's going to the stack and we're gonna throw it out, we send him into, for a power plant, they will call this air preheater. So the point is to heat the air coming into the furnace by the exhaust leaving the furnace. Okay, so that wheel kind of like rotate slowly, and when it's in the hot stream, it kind of gets grilled, you know, get a little bit hot, and then once it's hot enough, I mean, it's continuously moving, but it gets hot, and then it go to the cold side and start to cool down there. So it continuously moves the energy by capturing it in the material itself. It's a heat soaker, basically. Right? And so in the HVAC system, that happens in the cold, in the fresh air that you are bringing, and usually it's really hot in the summer or very cold in the winter, and the exhaust that you are sending away. Say you are in the hospital and they ask you to throw away all the exhaust. And you're like, man, but that exhaust is just air conditioned, that exhaust, and it's pretty good. But they have germs or what, or we have a regulation here, you have to send that flow out. And so in an attempt to capture some of those joules that you worked so hard to keep them, to create them, you send the air into those kind of enthalpy. Right? And there is also some design which, again, kind of not the chart were not really created for them, like plate heat exchanger. So you can see how in those heat exchanger, they just make them out of plates. Okay, very thin plate, but those plates are, as you can see here, kind of corrugated. Why corrugated? So that the flow going through them will be doing this. So the liquid will be like bum, 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 and he's like tuck, tuck, tuck. I mean, of course, slowly, because I mean, it's current. But he will have really good heat exchanger exchanging with the wall. Okay. So those plates, as you can see here, they can stack a lot of them and then make the hot fluid go into a bunch of those, while the cold fluid will be going in the other side. And of course, you need efficient, entrance and exit. But you can stack so much area in such a small plate, such a small space. But what do you think is bad about those guys? What is that? The gasket. The seal that you are creating so that you can stack them, that gasket needs to be really very durable. It needs to have a very good lifespan so that it wouldn't leak the liquid or the two fluids, right? So whatever the geometry, at the end of the day, there is a hot fluid and a cold fluid. And between those two guys, there is a bunch of resistance, bunch of walls or convection. And the total R is adding all those guys. Right? And the total R will eventually become UA. So 1 over R is UA. So this is the equation, right? And notice that you can define U based on the inside area, or you can define U based on the outside area, because at the end it's just like a resistance. So if you're gonna base it on the outside area, it's gonna be called U out. If it's inside area, it is UM. At the end of the day, you know, whenever they give you the area, they have to tell you, or whenever they give the U, they have to tell you what area they are based in. Or even better, sometimes they just give you UA together, right? And they tell you. All right, so based on this, you know, we were actually buying a bunch of heat exchangers recently for our research, and we went to McMaster car. They ship everything so quickly. Heat exchanger. And you can see the heat exchanger, the shell and tube, and the plate heat exchanger. So tell me, so this is basically you can see the prices are here, 3,700 all the way to 3,000. So if I want to buy this guy for $3,000, that's a 2 million BTU per hour. What do you think is wrong with this guy, with this? Here's the area, number of pass. So that's the number of tube pass, right? So he's a shell and tube. So there are like 4 tube passes inside. And I guess the shell side is this. You send the flow here and you come here. Okay. So, and stainless steel, that's pretty good. But can I, based on what we said so far, do you think it's really 2 million BTU per hour out of this? Like if I buy this for my boss and give it to him, will I get 2 million BTU per hour, or will I get fired first? Huh? Why? Why do you think it will give you less? So what is the ideal? But what? How did they calculate this 2 million BTU per hour?
Based on the minimum temperature and maximum temperature.
So you cannot write the Q dot without knowing the delta T. You cannot tell me the Q dot is 2 million, huh? I mean, you can control the U and the A, of course. You control the area by the fact that here is the pipe that we send inside this thing. And you control the U by basically saying, well, this is the prescribed velocity. But this T, TH minus TC, this is what determines the Q dot. So now if you read the small footprint, so the small blueprint, you will be able to, at one point, they will tell you, well, this Q is based on, if we click on the technical information, they will tell you we are basing this on, on a certain temperature. So they are using the cooling capacity is based on cooling 180-degree Fahrenheit processed water with 85-degree water. So if you have that difference, if you have 100-degree Fahrenheit, we can give you the 2 billion. So not 2 million, 2 million. The 2 million BTU per hour. But if you have only 5-degree or 10-degree, what will happen? So you give me the 100 here, I'm gonna give you the 2 million here. But you cut this to 10 degrees and you're gonna cut this by 10 too, right? It's gonna drop to 200,000. I added one more zero, did I? 2 million. Right, so you will end up with 200,000. Right? So you cannot size it without knowing the delta T it's going to operate at. Right? And that's why I was thinking about my friend, you know, like when they size, when they tell them we're going to deliver for you like a 7 horsepower or 10 horsepower, they have to say based on what temperature difference between the bus and the outside, for example, or between the refrigerant and the air. Make sense? Very good. So over here is saying that sometime when the wall is very small, UI become just U out because the area in and area out are the same. Imagine a thin pipe and why it's a thin pipe? Because we don't want resistance for our heat transfer. So if this pipe is just dividing the two fluids, then we will just make this very thin. And so then area I and area out will be almost the same. Why would we make the pipe so thick? Only if why will you ever make something like this? Pressure here is so high compared to the pressure outside. Maybe you would do something like this. And that's why if you take energy conversion next year, 4263, there is this power plant, it's called basically Ocean Thermal Power Plant, OTEC. And so for them to get energy from the thermal energy of the ocean, they need very hot water and very cold water difference. Well, hot water is on the top and cold water is on the bottom, right? And then they send the refrigerant or whatever the working fluid between those two locations. So one place is the boiler and the other place is the condenser. And usually the refrigerant that will boil at ocean temperature, and make steam or vapor so that we can turn the turbine is kind of like propane or butane, some kind of fuel. And so he would require very high pressure to be able to boil and condense at those temperatures. So we are talking about like 7 bar and 9 bar, kind of. So if we are at the surface, if this pipe is at the surface of the ocean, so that it's near the hot water on the top, and you are saying, I want you to give me 9 bar, I will have to make it like really hot, I mean really big pipe, right? And so that make it expensive. Right? So over there, a smart design, and I usually ask the student to do this every year, is to figure out, well, how can you still heat by the surface ocean, and it does not get really that hot, right? But I mean, let's call it 35 degrees C or something. How can you still heat your pipe by the surface of the ocean and with a fluid that is going to boil at, say, 9 bar, that's the fluid, and still have a thin pipe? Is that even possible? Because then we can reduce the cost of the pipes. So here is the surface of the ocean, waves are here, and you want to have a very thin pipe that can take 9 bar inside. How will this happen? I can't hear. Yes, very smart. If only we can make, that's the only way to make the pipe thin. I mean, you are stuck, thermodynamics, the TS diagram of that propane, you want to boil at this temperature, you better give me 9 bar, okay? So we are stuck here. So then the other thing that you can change is the pressure here. So how can you make the pressure here at 9 bar? Deep in the ocean, but the hot water only at the surface. Excellent. You got between the two, you designed the system. So what they do is that they take the hot surface water, send it down. Send it down how far? Rho GH, the pressure, hydrostatic pressure. So if I want to go 9 bar, I just need to go every 1 meter. So rho is for water is 1,000, G is 10, H is 10. Every meter of water is 1 bar. So all you have to do is go 9 meters. That's not a big deal. Go to 9 meters, and then over here, there is a circulating pump that sends the hot water in. And so over here at 9 bar, then your refrigerant can be an aerofoil, a very thin, a foil, a plate heat exchanger. Because he is at 9 bar refrigerant, but the water on the other side is also 9 bar. Okay, and the same thing for the condenser. So part of this Rankine cycle, it's a Rankine cycle that runs between 9 bar and 7 bar. The condenser, which happened to be from a very cold water coming from the down there when the sun never go, that guy will go up how far up? So 7 meters down. So the condenser will be here. So again, a circulating fan that take that cold water, right? And the refrigerant, that will be his condenser. And he will be running at 7 bar. And between those two guys, there is the turbine and the pump. Okay. Very good. So we would love to have, from heat transfer point of view, we would love to have thin pipes, thin heat exchanger, right? It's the pressure difference that make us go to a bigger wall, right? And we go through all those tricks in order to be able to minimize that that pressure difference across, right? So when we design or try to pick a size, that table will probably be your best friend, because the question that always comes, say, in the next project would always be project 4, would be like, I don't know what U should I use. Like, so what you can go to McMaster. Okay, I don't see any U over here. How do I get the U? They just give me the price, they give me the BTU, and they give me the area. How can I get my overall heat transfer coefficient? Delta T, Q is UA delta T. Yes, so we know that delta T, they base this thing on, right? We know that they said when you are cooling 180 with 80, then you'll be able to get your E, right? Because you have the Q dot and you have the area. But also that table can really be very useful, because that table, but the problem with that table is that kind of like have big range. It tell you if you have water to water heat exchanger, your U is between 800 and 1700. So I mean, is it like 1500 or 900? What is it? Right? But at least it gives you the order of magnitude. Right? So this is a typical number of the overall heat transfer coefficient. Notice that the U have the same units like the H, because 1 over UA is written in the same way as 1 over HE. So what is the unit for the H? Watt per meter square Kelvin, right? So it's the same as here, watt per meter square Kelvin. And that Kelvin part remind me of something that I always get questioned about. So this equation, UA delta T, the students say, you know what, should I use degree C or degree Kelvin or the Kelvin when I calculate my delta T? Doesn't matter because you are doing subtraction, right? It's the same. So don't worry about the units. This is the one exception to worrying about the units. Otherwise, be scared of the units. Okay, and we talked about this earlier today, how like we had filled area, and the surface area. The filled area is not all of it, The filled area is only efficiency of it, right? So eta fin multiplied by A fin, depending on the geometry. Is the fin look like this, or the fin is like really tall like this? Right? And you notice here there is an extra resistance added on both sides of the pipe, and that is fouling. So fouling is, depending on how clean your fluid is, you will start having layer and layer of deposits, especially at high temperature, especially with a little bit salty water. Like our water is not totally, without salt. It has some salt in it, and at high temperature, those basically deposit making scales. And so one should expect an extra resistance in the bus. It's one more thing that will slow down the heat transfer, depending on how clean it is. Right? And those are the typical, R for like different fluid: alcohol, vapor, refrigerant, foul, fuel, oil. All right. So this equation, this is not heat transfer, this is just servo, and this is servo. And this equations is always correct, always true, no matter what is the configuration. What does this equation say? Q dot is m dot Cp delta T. Q dot is m dot Cp delta T, right? It's basically how much joules you are. This is coming from what? First law. The first law that say Q dot is m dot delta H. The delta H for compressed liquids, Cp delta T. When we are on the TS diagram on this side, we call this the what? The compressed liquid side. So, you can calculate H1 and H2 if you know two property. And also, even if you know one property, what did I say in the office hour last week? Because sometimes the compressed table is not generous. There's not that many lines.
Use the saturated.
At the same pressure or temperature, so I want H1. Should I use this, which is HF at the same pressure, B1, or should I use this, which is HF at the same T1? And B1 and T1, I'm referring to this point. Should I use at the same temperature, or should I use at the same pressure? Same temperature, yes. And why would I remember this? Or how could I not forget this? If you look at the TS diagram, you will see that what am I plotting? Pressure lines. So I am in purpose trying to make them so close over here, because that they are. If you look at the actual TS diagram, you will see things that are really on the surface. So today in the exam, if I ever told you plot the TS diagram of a cycle or something, and you did this, Women will take points off. Why? Because they are already on that red place, right? I know that I always plot when I'm like trying to make a sketch or something, and I'm trying to show you the pump work. I do this, right? And I say, well, here is 1 and here is 2. I have to, because I want to show you how the line is on top and how it's isentropic pumping. But in real life, or in the actual TS diagram, how things will look like. Everything is here. So point 1 and point 2 would be like here 1 and here is 2. You get me? So this get plotted basically like this. Right? You plot everything, gets plotted. Here is 1, here is 2, here is 3, here is 4, here is 5. That is the right way to plot them on an actual TS diagram. But if you want to make a sketch to explain to the people how there is a pump, you know, you are trying to explain to the customer or to your students, you know, how pumping is happening, you basically have to do it like this. But if I say plot on an actual TS diagram and I give you the actual TS diagram, you have to put them all on that line. Does this make sense? Now, they have to be plotted on the place where they are. And that place, everything is here. So back to our discussion. So if everything is on that line, it's obviously, if point 1 is here at P1, which say happen to be here. This is B1, right? And at T1, which is actually here, which point will have the same enthalpy like it? Of course, it's the one here, not this guy. Why would the guy all the way up will have the same enthalpy? But the guy that I cannot tell them apart because they are on the same point almost, that's the one, right? That's the one. So that's why we can approximate the compressed liquid enthalpy by HF at T1. So what are we saying? We are saying the enthalpy is function of temperature only, not pressure. I mean, it is function of pressure and temperature, but a very good approximation that it's function of temperature only. And therefore, I can really say it's CBT. So this, which you probably have seen in Thermo 1, is not contradiction to the fact that we say H is H of P and T, right? This is the absolute truth that H is function of B and T, and go get your steam table or X steam and enter your pressure and temperature or pressure and entropy or temperature and entropy and get your enthalpy. But this is not that bad at all, especially, and that is why we have to go to the steam table sometime, especially that what? What? Especially what? What's wrong with the CP? Anything bad about the CP? It's not constant. The CP is function of temperature. I thought that CBU of water is 4186. That's what I memorized in high school even. 4186, right? Joule per kilogram Kelvin. Well, that is at room temperature. But when you start going up and down, that's why what is your right CP for water, right? And so that's why it's more accurate to do this, right? And then second level accuracy is at least get the HF at the same temperature. So you have the same temperature range, your CP will be pretty good. So the H is pretty good, right? And then third option is to get a CP that is a good average in that range. So when I back to the heat exchanger, right? When I see a heat exchanger that's going from this to this, well, in that range, there could be a CP that is a good average for this temperature. Like he come at what, 80 Fahrenheit, and he leave at say 130. Okay, so what is the CP around 160, 170, and that, or 150? That would be the CP that I would use. Right? So we need an average, a good average CP. But at the end of the day, whatever this guy lost, we can write it as M dot CP delta T. Here's delta T. So if this was the hot fluid, then, and by the way, Q dot hot is the same as Q dot cold, right? Whatever this guy gain, this guy lose, assuming the air outside does not get anything, assuming the heat exchanger is like really insulated, right? So when you go to the HVAC lab in Stillwater, they had this big psychrometric chamber, and you see all the piping and stuff, you see like they are insulating the pipes like crazy. So much insulation because they don't want the measurements to go bad. They just want the hot and the cold fluid to basically only exchange heat with each other. They don't want anything that leaves to the outside, right? So M dot cold, CB cold, delta T cold equal M dot hot, CB hot, delta T hot. Okay. So knowing T1 or T hot N and T hot 2 and M dot CP hot and one of the temperature, let's call it TC out, will immediately tell you the force one, right? So knowing 3 of those guys is good enough to get the force one. So you cannot just know 3 temperature. If you know 3 temperature, then you know the force. Okay? Make sense? But you can be in a situation where you know only 2 of them. Like, for example, you know THN and you know TCN. But you don't know how hot, what's the TH out, that you don't know, and you don't know TC out. So this 2 category of problems is what will determine should you use the logarithmic mean temperature difference or should you use the effectiveness method. If you know all 4 temperature, or actually 3, that's as good as knowing 4. You go for the logarithmic mean temperature difference. It's become so easy if I know all the temperature. But if I know only 2 temperatures and I don't know the other one, the other 2, then I will use the effectiveness method. Okay. Can I still use the logarithmic mean temperature difference if I know only 2 temperature? Yes, but it will be an infinite try and error. I mean, not infinite, but you have to do try and error for it. So it makes sense to use the method that gives you the solution immediately, which would be the effectiveness method at this time. Good. All right. So in the heat transfer book, then they did something like really, I would say, stupid. Okay, they added, they multiply M dot C, M dot CB together, and this new quantity, they call it also C. I mean, out of all the letters that we have in the alphabet and the Roman alphabet and everything, you could have used anything else, but they end up using C for it. So then people get confused when they see that big C. Is that the heat capacity rate or is it the CP specific heat rate? Like why? Why did they use C? But they did. Okay. What's even fun or sad, actually, so you got CH and CC, right? C hot and C cold. M dot CB cold is C cold and M dot CB hot is C hot. What is even said is that they divide the 2 of them together and that ratio between capital CH and capital CC, they would call it also CR. I mean, it's like the perfect, you know, I don't know what we call it, perfect conspiracy to confuse students. Like, why? Like, just call it D or R ratio or something. Anyway, so we have to be smart when, or alert at least. I mean, you cannot solve this problem half asleep because just too many C's in the problem. So we got CB hot and CB cold, that's the specific heat. The one that you would say Q is M dot CB delta T. And you got capital C, the heat capacity rate, and you can do that for the hot or the cold. All right? Make sense? So the only time when you cannot use Q dot is M dot CB delta T is this case. What is that case? How come one of the fluid is not changing its temperature? I mean, I see the hot dropping, but the cold is just constant. How is that possible? And the same here, look at this. The cold is increasing its temperature, but the hot fluid is just staying the same. You keep giving him joules, and he doesn't want to go up in temperature. Why? How is he using all those joules? Where does all those joules that, I mean, it's clearly I'm giving him joules. Yes, he's using that Q dot to turn his liquid into vapor. So that is boiling. And the same thing over here. He's using all this Q dot H. Sorry, Q dot C, which is M dot Cp delta T, hot. He's using all that Q that is being sent to him to basically turn his liquid into vapor. So that happened at constant temperature. So this is actually very important point to make, that when you are boiling a liquid, okay, when you are boiling a liquid, say by cooling hot gases, there are hot gases coming from the furnace. They are coming at here, and they are cooling. While doing what? While your water that you deliver to the boiler like this, it basically will stay at the same temperature. So if this was my heat exchanger, it's kind of a shell and tube heat exchanger where the fire go into those pipes, okay, and those pipes are sitting in a tank with water. So there is water everywhere over here at high pressure around those pipes. So that water will start bubbling on the tube that has fire inside, hot gases inside. And vapor will leave, but while this process is happening, the steam that's leaving cannot get hotter than T saturation until it's all vapor, until he leaves the droplets behind, leave the liquid behind. And now when he is like just vapor by itself, now if you have another heat exchanger or another tube, then that saturated vapor can do this, can start become superheated. But with, say, the incoming hot gases. But until you leave all the droplets behind, you will never be able to change your status. You will never be able to change your temperature above desaturation. You have to finish all your liquid, become saturated vapor, then you can change and go to higher temperature. Huh? Make sense? So in this scenario, when one liquid is doing this, one fluid is doing this, while the other one is doing this, for the one that's changing its temperature, yes, Q is M dot Cp delta T. But for the guy that is constant temperature, the Q dot is not going to be M dot Cp delta T, otherwise I will have delta T 0, it is 0, and Cp will be infinity. So instead we use what? M dot HFG. See how? And then you can figure out how much M dot is being converted to steam from this equation. So the whole joule is turned into M dot HFG. And that also gets applied to, say, melting. If you have like liquid that turn into, if you have solid that turn into liquid, you have to do this. All right, there is 10 minutes left, and I want to start the exam at 7 so that we finish at 8, and you'll have 10 minutes for uploading the file. So let's have a 10 minutes break, and when you come back, you will find the exam uploaded to the campus. 10 minutes break. We'll start again at 7.
So we have to have submitted in Canvas by 8:10.
So we'll finish the exam at 8, and you have to upload everything before 8:10. Any minute after 8:10 is 10% off. 10% for every minute after 8:10. And I don't waive this, like no matter what is the reason. Computer blackout in Tulsa, nuclear holocaust, I don't care. 8:10, any minute after 8:10 is 10%. Yes.
Would we be expected to write on any actual diagram?
That's an excellent question. Let me answer it when they come back. This is a very important question. So the question, what do in online people need to do? Just turn our camera on when the test starts. That is correct. Online people need to have their face showing up so that I know that they are not talking to anyone else. I'm gonna upload it and it should be available at 6 o'clock. Sorry, at 7 sharp. So for online people, do we need to unmute ourselves? No, you don't have to unmute. You just need to remove, you need to the camera to be on showing your face. Do we need, are you gonna give us table or do I need my book ready? Well, you have the whole internet. You can get the internet. You can get the tables from the internet, steamtableonline.com. You can also use the Xteam, right? That also work. And I uploaded the exam under assignments. So if you go to assignment, you will see exam 1 and it will be available in in 4 minutes, at 7 o'clock, it will be uploaded. So one question was, are we expected to write on the exam paper? Are we expected to actually write on the exam paper? So a lot of you don't have papers on you, right? So if you have, here is the part that I would actually expect you to write, but you don't panic yet. On plotting that on the TS diagram, I actually give you to the TS diagram, and I say plot on that TS diagram. So you can, on the Word file, or in the PDF, you can draw lines on your screen on it, right? And in case that's very hard for you to actually draw on the screen and take a picture, you can just put your paper on the computer and trace it, right? So I just need that sketch to be perfect. So either draw on the PDF file, okay, and I'm actually gonna email the figure for every one of you too, so that you can, as a Word file. If you print it out, you can write on it here and take a picture. How did you print it out? It's not ready yet. You have a TS diagram from before, okay. Yeah, right. That works too. So some people have actually already a TS diagram on paper. So that works. If you can write on the one on the screen, that works. If not, you can just trace it on the screen. I just want a TS diagram that looks like the real thing, not a sketch. Understand what I'm saying? I'm gonna email the Word document, or actually just upload it to the assignment as well. Let me upload the Word document as well. Or email, I guess. Let's do it by email. Right? So in 1 minute, you should be able to access it, and in your email, I'm gonna send the exam in Word file as well. So that you can go there and draw in Word. Lines, basically. All we need is just lines to plot the TS diagram. Good luck, guys. Don't be scared if it's long. It's long on everyone. Right, 7 o'clock. You should be able to click on it now. Under assignment, you should be able to see it. Did it download?
Mine just keeps saying error while downloading document. I
Okay,
can't see it.
so maybe I should email it to you guys then. Let me email it to everyone. Don't panic yet.
Okay.
Exam 1 in the mail. And I can also upload it just to the place where we keep our homework and stuff. I will do that too. Right, so exam 1 is in 3 places now. They are under the assignment, and it's also under the place where we keep our homework and stuff, and it's in your mailbox. Figure 1 is also sitting there. The question is, can I use a TS diagram that does not look like the one that you emailed? No, it does not matter.
I have a question real quick.
Yeah,
So you said on problem 1, so I didn't print it out. So on problem 1, how would I draw on it if I didn't print it out?
you draw with pencil or ink or whatever. But use a ruler. For isentropic stuff, use a ruler, right? So that look nice.
So if I already have one that's printed out, I can't use it?
You can, if you have one printed out. We
Oh,
we are
okay.
plotting the cycle of it.
Okay, because I have a regular, okay, all right, then I might just go print that one out then. Okay, thank you.
So the whole idea is that when you put state 1 and 2 and 3, I want it to be in the right location, exactly, in the right pressure and temperature. Not anywhere. That's what I meant by actual TS diagram. Not a cartoon, but T1 is exactly where T1, B1 is exactly where T1. You get me? Like I cannot put the condenser line anywhere. It has to be exactly at the temperature, 50 degrees C. You have to land exactly in the right place. Suzanne, I cannot see your face. You're too low. Can you lower the camera a little bit? Thank you. So Gabriel, I don't see your camera. Can you please put your camera on?
It is on though, but I'm not sure what's going on my end.
Yes.
Is it correct that on problem 1 of the temperatures of the high temperature turbine and the low pressure turbine are both 1,000 degrees Fahrenheit?
So the question is in problem number 1, let's say high pressure turbine and low pressure turbine both have 1,000 degrees. Is that an error? No, it's not an error. It's correct. So the question is, but the chart that it's in Celsius and you are giving us the temperature in degree Fahrenheit. Yes, I'm a mean person. Yes. I mean, that is what you expect in practice. They will give you things in Fahrenheit and you have to do calculate in degree C. So I'm just making you experience that problem.
Am I allowed to leave real quick, go print out the first page?
That's okay.
Okay.
It doesn't say how far the temperature goes down before it goes to reheat. Is it allowed to pick any temperature?
So the answer, the question is how low we should go. And I'm not going to answer that question. Another question saying the condenser is given in degree C and the other guys are given in degree Fahrenheit. Yes, that's not an error. That is done on purpose. Yes.
All the problems with 5 points?
Are all the problem have the same weight? Yes, each one of them is 5. And that's why you don't spend too much time in one problem and leave the other one. They're all equally important. Victor, we cannot see your face.
I don't have a camera.
Then you shouldn't take the exam. Sorry.
Okay, so the figure that in the email, because I was gonna just mark on it, it does not look like the one that's actually on the exam. And I don't have a way to print this.
That's weird. I think they are both identical. But anyway, any true case diagram will work. I'm gonna grade basically on is the point are in the right place with the right pressure temperature or not. That's all the point.
I'm just
When you
saying,
have
how am I
point one or
supposed
point
to?
two, it needs to go exactly in the right place.
I'm just asking how I'm supposed to mark on this. Because if I can't do it from here, I was gonna do it on my tablet, but this is not the same picture.
You can do it on your tablet, you can do it on actual paper, you can do it on Word. That's why I emailed you the Word file by drawing line in Word.
Okay, I'm trying.
I also uploaded the document file to Canvas. If you go to Canvas, you'll find the document file sitting there. "30 minutes left."
On problem 2, we're trying to find M dot BFPT, correct?
Correct.
Where is that coming from?
If you look at the top corner, top right, left corner of the figure, you'll see it's coming from a point called X, right?
Yep, which is in the middle of a line, I think.
So point X, you will see it's coming from the low pressure turbine, right?
Mm-hmm.
That X is that X.
Okay.
15 minutes left. If there's a problem that you didn't solve until now, now's the time to actually go and touch that problem. Don't leave any problem without attempting it. Sorry.
Do we know how much is entering the low pressure turbine to begin with?
Are you talking about problem number 1?
Problem number 2.
Do we know how much? I mean, you can read the chart. The chart
Okay.
will help you. Five minutes, guys. Question, can we leave if we are submitted? There is no quiz today. No, there is no quiz today. Exam is enough. You can leave. Thank you. Don't forget to write the pledge on the first page and your class number and if you are Zoom or in the class. Write the pledge that you didn't help. Any other you didn't copy from check.com. Time is up. We have 10 minutes to upload the paper. Any minute after 8:10 will be 10% off, no exception. So please act now, start copying now. Take a picture and upload it. Yeah, you can use this and take a picture. What? There are people taking the exam here. There are people taking the exams here. Good night. Yes. Yes. 8:05, 5 minutes. Please don't miss the deadline. 10% for every minute.
No, I managed to upload it, but it didn't do very well.
Bad things happen and we'll figure out a way, not just you, other people will have problems. We'll figure out a way to be fair to them. Don't worry so much. For now.
Is there any homework this week?
Yes, sadly. I'm gonna upload it. Bye. Okay, 3 minutes. If you didn't upload so far, I feel nervous for you. $8:08.
All right. Have a good night, Dr. Call, or excuse me, Dr. Salam.
All right, good night. $8:09. Bye.
Next time, if it's going to require a chart or graph that draw on that's provided, they could, or we are notified with the chart.
See that again?
So like the TS diagram, you want to do exactly on the chart. If
Yes.
that chart be provided in a physical form
Rather than on the computer,
rather than. a computer.
right? Because, but you have a computer.
I understand that, but trying to write on the computer
It's really hard to draw lines.
is quite harder to do the line. than
Okay,
Just getting a piece of paper tracking the mark,
right, right.
and it takes a lot more time to be able to get all the files.
You have a point, yes. But you know, drawing lines on Word is not that hard. In Word document, you just say insert line and then you can put the line anywhere you want on the figure. Have you ever done that?
I have, but.
It's not that easy.
Pen and paper,
Okay,
especially if it's on the chart. I'm not saying that you physically have to provide it, but if it can be notified. Hey,
so we can print it earlier on. Okay. And we are done. It's 8:10. Good job, guys.